Yeah, okay. Welcome back, everyone. So the next and the last session for today, we'll have a lab session, and we have with us Mayur Shivamurthy, who is a PhD student at IIT Dharwad. He did his MTech in NIT Goa and then joined for PhD here in 2018. So he's completed about 3 years now. So he'll be discussing the spice simulator, and we'll go through an exercise on how to design a two-stage op-amp. I hope you have been able to install ngSpice on your computers and run some test programs. So for this session, what we have done is, given the short time of 1.5 hour we have, it is difficult to actually go through the entire design and do it yourself and simulate it completely. So what we have done is we have created an exercise problem, like a tutorial with the solution netlist and the solution and the design procedure, along with this presentation which Mayur is going to show you right now, is all available on the web page for this course. So you can just download and keep it. So Mayur will explain how the simulator works, what is the design procedure of the two-stage op-amp, and show you a simulation of the amplifier itself. Thereafter, we have given you a few exercise problems wherein you can just change some values in that uh, netlist, and to understand better of how the performance changes when you change the values of certain components. Okay, so that is how we will go on with this lab session. With that, I will hand it over to Mayur. Mayur,
Yeah, thank you, sir. So, am I audible?
yes, you are audible.
So, the screen is
Yes,
visible.
yes, it is visible.
Yeah. So, good afternoon, all. So, as sir discussed, so first we'll look into the introduction of this SPICE simulator. Uh, so, what is SPICE? So, SPICE stands for Simulation Program with Integrated Circuit Emphasis. So, it is basically used for simulating circuits for verifying performance and optimization. So, and it's a powerful simulator with the industry standards. So, which all the advanced EDA tools use this particular spice, and it support different type of analysis like AC, DC, transient, noise analysis, etc. DC operating point analysis. Why spice is required? Because as we know, the circuit gets more complex with increasing number of transistors, and analyzing these circuits with analytical and mathematical expression is very difficult, and it is impractical also. So that's why, so even for the smaller circuits in scale technologies, the number of parameters are also too high, because if we see a simple BSIM 4 NMOS model file, it has about 39 technology dependent parameters. So that's why, in order to make our analysis easier and to understand this thing better, so we go for this spice simulators. So if we see the skeleton of a spice code, so it has a title line, then it contains a circuit description, which is basically a netlist. Then comes the model statements, then analysis commands, output commands, and this is my dot end, because every spice code must end with dot end. So as I told, the title line, it will be ignored by the simulator, and any comment line in the spice code will start with this star. So, and multiple files can be included in the spice using dot include directive. Okay. So even you can add your subcircuit file as well as model file with the dot include directives. So what are these analysis command? These analysis command will include transient analysis, DC analysis, AC analysis. Okay. Then the output command must begin with dot control directive and terminates with dot nc directives. And commands which are not written in dot block must proceed with dot. Okay. So we will see an example how all this works. So then the output commands are used for saving and plotting your outputs. And the program, as I told, the program file must end with dot end directive. So the circuit description. So let us come to the circuit description. So the circuit description in SPICE is called a netlist, which consists of element and source description. So any element description is form of a letter followed by a name, that is then different nodes associated with it. and model names and parameters values. For example, the resistor is defined by R, so it can modify R1, R2. Okay, capacitor is C, inductor is L, switch is SW. Uh, K is for inductor. So M is for MOSFET, Q is for BJT. So when we write the MOSFET, the convention is it is the node starts with a drain, followed by gate, source, and then substrate. Similarly, for the BJT, the convention is so Q followed by the name, for me Q1, Q2 or something. Then it starts with collector, base, emitter, and substrate. Okay. In some case, you can ignore this. It depends upon what type of model files you are using it. So then coming to the sources, we have independent sources and dependent sources. So voltage V refers to the for the voltage source, and these are the two nodes where it is N plus N minus, whether it can be a AC or DC, and what is the value. Similarly, I for the current, and also we have a dependent sources. So G for linearly voltage controlled current source, E for voltage controlled voltage source, F for current controlled current source, H for current controlled voltage source. Okay, and also this SPICE supports various non-linear dependent sources also. So you can refer ngSpice manual for more such type of sources. So let us first see how to write a netlist for a given circuit. So as I told, the first line anyway, you can write a first line. So this is not an entire SPICE code; it is just example how it can be written. So in the next slide, we will see the full SPICE code. So this R1. So first you should have a circuit diagram ready with all the node numbers labeled. So R1, that is resistor R1, which is connected between node 3 and 1, whose value is 1 kilo ohm. There is a capacitor C1, which is connected between node 2 and 3, whose value is 1 pico. M1, there is a MOSFET M1. So as I told, the convention is drain, gate, source, and substrate. Then what is this? Let us see. This is basically a model file name, that is CMOS N, and that is a model that we'll discuss later. So CMOS N is the model file name, and these are the typical, that is the dimension of the MOSFET. So W is equal to 2 micrometers, L is equal to 0.18 micrometer, and there is a voltage V1 which is connected between node 1 and 0, DC voltage source with the value of 5 volts. V2 which is connected between 2 and 0, it's a sinusoidal voltage source whose varies from so 0 to 1 volts with amplitude of 1k, and there are different parameters like phase, offset. Okay, so this what are the this the convention can be seen in the way it can be written can be seen in the ngSpice manual also. So next comes the analysis command. As I told, dot dc dot ac dot run. So this dot dc is for the dc analysis. So if you want to vary the source, okay, vary certain voltage and see the behavior with respect to this particular source. So you begin with dot dc, the source name, the starting voltage and the stop voltage. That is to till what range it has to be varied. This source name, and with what step size it has to be varied. So next comes the dot analysis for AC analysis. So dot AC. Okay, this dot corresponds if you are not writing within the dot control statement. Fine. So dot AC. So it can be of a decade or octave or in a linear. So number of points. Okay, number of points you are needed for plotting, and the starting frequency and stop frequency. So example is dot AC. It is in decade plot with 10 points. So 10 hertz to 100 megahertz. Next comes the transient analysis. So that is with respect to a time, x-axis being a time. So dot tran is the keyword here. So the step size followed by a stop time. If you want to specify the start time, it's the start time. If steps time is not given, it will take by default simulation step size. Okay. So these plot commands are for plotting voltage. It is basically plot V of 1, that is plot node 1 voltages, node 2 voltages. Okay. Then there are current plots also. Okay. You plot V of I of voltage. So that next we will see. So these are the certain example for output commands. So let us see the ngSpice code for a simple RC circuit. So this is the circuit diagram what I have, and to this particular circuit at node 1 I'm applying a PWL signal, okay, which goes from 0 to 5 volts. Okay, so the first line, that is RC transient response, it is the first line in the spice code which will be ignored by the simulator. So then comes the net list. So you can see there is a resistor R1 which is connected between 1 and 2 with a value of 1 kilo ohm. There is a capacitor C1 which is connected between 2 and 0 with a value of 1 microfarad, 1 U. Okay, it's micro. And there is an input, a PWL voltage. So linearly piecewise voltage. So it's connected between 1 and 0. So 10 millisecond is this is the initial start time. That is time corresponding voltage, time corresponding voltage, time voltage, and time voltage. Fine. Now, next we will do the transient analysis. As I told, if this tran is coming in the control command, then no need to put dot tran here. But if you are writing above the control, so you should start with dot tran. So it's 0.02 millisecond. That is my step size, and the stop time is 20 millisecond. So then we'll plot the voltage. That is plot V of 1, V of 2, that is voltage at node, voltage on node 1, node 2, and the current through the voltage V1. Okay, this dot NC. So dot control must end with dot NC followed by dot end. So for the same thing, we'll do the AC analysis. The net list remain the same, but what happens in V in 120 DC 0? I'm giving and specifying an AC. Okay, AC magnitude is 1. Then dot AC, so it should be in a decade plot, and 10 points. So start frequency is 1 hertz to 1 mega. So 1 mega is the keyword for here, MEG. So then dot control. Then in the dot control, you should plot the magnitude in dB. So this plot VDB of 2, that is voltage at node 2 in dB. And the phase plot, so normally this phase plot will plot in a degree, so we'll convert this radians to degree and then we'll plot phase. Okay, so this is for the calculation purpose. So this is how we plot the magnitude and the phase plot. Then next comes the sub circuit. Okay, the sub circuits will be very handy and very useful when you're instancing when you're writing a very big circuits. So for example, a regular circuit can be described using repeated instance. So you can instantiate this block it is required. Okay, so if you see the sub circuit description, so dot sub circuit, so nodes and s name, so that is a this thing. So how you that how you declare, so followed by the net list and dot nds and s name, that is the sub circuit name. Fine. So let us consider a simple resistive divider. So this particular resistive divider, I'll be using it as a sub circuit. So let me define the sub circuit. So dot sub circuit. Then the name of the sub circuit is V divide, and the nodes which can be accessed and are 1 and 3. Okay, the nodes which can be accessed in the main circuit is 1 and 3. So within this, let us write the netlist. So R1 connected between 1 and 2, the value is 10k. R2 is 2 3 and 5k. So dot nds V divide. So n dot nds V divide is the name of the sub circuit. So when you instantiate this particular sub circuit, it should be instantiated as X. Okay, X is the predefined word. So X with any name, 1 or div. So in the main nodes, this is 8 and 10. So which means 8 will be mapped to 1, 10 will be mapped to 3. Okay, and this is my this thing. Okay, sub circuit name. So we can use this sub circuit for an example using 741 op amp. So if we have the sub circuit for a 741 op amp, So that subcircuit file I'm using some dot include file. So this ua741.txt, it has the subcircuit netlist of this particular op amp. So just I'm calling it, I'm adding it like dot include. So then followed by x1, so x1, then 0 1 2 3 4, so 0 1 2 3 4, and followed by the name of the subcircuit, that is op amp. Then R1, that is resistor current between 5 and 1, 1 kilo ohm. C1 between 4 and 1, that is 0.1 microfarad. So the same thing again, the supply voltages. The rest all part remain the same. This is the transient analysis, and we are plotting V5 and V4. So next thing is the dot model statements. So when you take any MOSFET, so it has many parameters, right? Like oxide thickness and parasitic capacitance, CGS, and threshold voltage. So all these, they are maintained in separate model file. So those are in the dot model file for the corresponding MOSFET or for a BJT. These parameters are defined at a dot model and assigned a unique model name. So the format is model name, and what type it is, whether it is an NMOS or a PMOS, and P name, that is different parameter value. So there are two ways to include this model file: either specify the model in the main netlist, or the way we have declared the subcircuit file, use dot include statements. So the two things we have shown here. So for this circuit, we can include this model file as this. So M1 is the transistor which is connected with this. These are the drain, gate, source, substrate terminal. MOS N. So you can see here, MOS N is the model file name. Okay, for this particular NMOS, and level 8. So because PI supports this particular model file. So R1 3 2 1. The rest part is the same. So these are the netlist for the circuit. And or else instead of writing in the main circuit, you, if this model file is written in a separate file, okay, you can just include this statement like dot include tsmc model dot txt. So if you know, so for this particular, in this model text, so for an NMOS, CMOS N is the model name here. In this, I can write it as M1 2100 CMOS N. That is, I'm taking NMOS model and I'm giving the geometry. So W is equal to 2 micrometer, L is equal to 5 micrometers. So rest are the netlist, which is very evident. Similarly, you can write the netlist for a CMOS inverter also, the same thing. So I hope this writing a netlist in the SPICE is clear. We'll move to the op-amp design now. Okay, so any questions?
Hello, sir.
Yeah.
Uh, for the after writing the entire script, what the command we need to give for the simulation to observe the graph?
So, sir, for example, if you want to do a transient analysis, so plot is the command, sir. Plot, for example, you see, if you want to do a transient, you should give dot tran.
No, no, Mayur, I think the question is how do you execute the netlist? How do you run the netlist?
Yes, yes.
Okay.
So you will be showing it with the op amp?
Yes, sir. Yeah, I'll be
Then we
showing
can
it with
just.
the.
Okay.
Uh,
So, Mr. Dipesh, what we will do is Mayur will take us through the design of the op amp, and he has a netlist for the op amp.
Okay.
When we run that, we will see how to execute the netlist.
Okay. Okay.
okay. The okay. Sir, is the screen visible, sir?
Yes, it is visible.
So we'll design a simple two-stage op-amp. So first thing is the specification is given to us. So the specification for this particular design will be the open loop gain, which is greater than or equal to 60 dB. Slew rate, it is 20 volts per microsecond. Gain bandwidth product of 10 megahertz. And the required phase margin is 60 degree. Input common mode range is zero point 0.9 volts to 1.6 volts with a load capacitor CL is equal to 10 picofarad. So before beginning our first cut design on pen and paper, so these are the different parameters which are required. Let me make clear to you that we are using 180 nanometer technology, TSMC. So for that particular technology, so the threshold voltage of NMOS and PMOS is taken to be zero point 0.4 volts. Kn dash, it is current factor for NMOS is 218 microampere per volt square, and Kp dash is 90 microampere per volt square. So this is the circuit diagram. This is the circuit diagram, and this is a two-stage Miller seated op-amp. Uh, so as you know, as that for this this is the transfer function for this, which has two poles, and this CC will do the pole splitting, where P1 is the dominant pole. So that is G01 G02 divided by CCGM2 is the dominant pole, and P2, that is GM2 by CL, is the second pole, so which is on the higher side. And because of this CC, there exists a right hand side 0. So the value of right hand side 0 is GM2 by CC, so that is in the right half plane. And K is, that is the DC gain, so GM1 GM2 divided by G01 G02. So where G01 is the output conductance, it's here. So here this thing, so where G01 is equal to G02. uh, so, so, uh, okay, this is the block diagram. So first, while designing, first we'll design for CC now. Okay. Since we know the load capacitor value CL is equal to 10 picofarad, uh, so in order to have a phase margin of 60 degree, it is required that the compensating capacitor CC must satisfy this particular condition. So this condition is coming from the analytical and mathematical value for the phase margin, which we want to be 60 degree. So choose CC to be equal to 0.2 CL. So hence, since my our CL is 10 picofarad, the CC is evaluated to 2 picofarad. So once this CC is evaluated, next from the CC we will evaluate the slew rate, because for the slew rate is given by I naught divided by CC. So slew rate is known to us. CCs we have calculated from the previous step. So from this, I naught is evaluated around 40 microamperes. Now, so once I naught and CC are evaluated, next thing to evaluate is GM1. So we know that unity gain frequency, that is GBW, is given by GM1 divided by CC. So this is in radians per second. So if we convert it, you can convert it into hertz, fine. So omega is equal to 2 pi f. So we know the value of CC and we know the value of GBW, that is unity gain frequency required is 10 megahertz. From that, you can calculate the value of GM1. So what we get from GM1, because GM1, from this GM1, we can calculate the dimension of the input transistors M1 and M2, okay? Because GM1 is it is equal to square root of 2 ID mu n so x W by L. So solving for W by L for 1, 2, so we get GM1 square divided by I naught into Kn dash. So we have assumed the Kn dash, it is known to us, it is 218 microampere per volt square. So W by L for 1 and 2, that is M1 and M2, is evaluated to 1.811. So this is that aspect ratio we want to get this particular GM1 for a given current I naught of 40 microamperes. So with L is equal to 1 micrometers, so I'll approximate that my W1 is 2 micrometers. So this is for the first cup design, because once you simulate this, again you have to adjust this W ratio. Fine. Now, next, once we have determined this M1 and M2 dimension, next thing is to determine the dimension of this tail current M0. Fine. So how to do that? Okay, so we have finished with this thing. So let us go to the dimension of W by L of M naught. So that W by L of tail transistors is obtained from the input. It is the minimum common mode input voltage. So that is what will be the value of this voltage for which this transistors will remain in saturation region. Okay, because as this voltage decreases, this particular transistors will get out of saturation and it will get into linear region. So what is the minimum value required? Okay, so we know that input common would range from 0.9 volt to 1.6 volts, right? So the minimum is 0.9 volts. So from the 0.9 volts, so we know that V bias, this thing must be greater than equal to VGS1 plus VDS0. That is, this voltage, this VB, this thing bias minimum must be equal to the drop of this plus drop of this. So VD sat is the minimum voltage which is required across the transistor M0 such that it remains in the saturation region. So from this VD S0 value, we can determine the value of the geometry of this particular transistor M0. Okay, so here are the equations here. So I will be calculating the value of VDS0. So the VDS0 is equal to V bias minimum minus VTN minus square root of I0 divided by Kn dash W by L1. Okay, so the VDS0 is evaluated to 0.2 volts. So from this VDS0, we will calculate the dimension of M0 transistor, it is current transistors. So W by L of the tail current source, it is I0 divided by VDS0 square into Kn dash. So with with L is equal to 1 micrometers, my W0 is evaluated to 9 micrometers. So the same dimensions is applicable to the MC0 transistor also, right? Next, so once those transistor dimensions are calculated, next we'll calculate the dimension of 3 and 4, that is the top PMOS transistors. Okay, these transistors 3 and 4. So we have calculated M1, M2, M0, the tail current source, and the CC. Okay, so so how to calculate W by L3 of the top PMOS? That is from the maximum input common voltage range. So it is again the same principle. It is required that M12 must remain in saturation region. So this must remain in saturation region. So for that, what is the maximum voltage that you can apply? Because as this voltage keep on increasing, there is a possibility that M1 may get out of saturation and get into linear region, right? So from that condition, we will determine the dimension of M3 and the M4. Okay, so that is here. So from the maximum input common voltage range, so that is from there I'll determine the VD sat for 3, that is VDD minus VD minus VTP. We know all these values. So VD sat 3 is evaluated to 0.2 volts and hence W by L3 is evaluated. So this is the expression, that is W by L3 is I0 divided by VD sat 3 whole square into Kp dash. Okay, so W by L3 is evaluated to 11.1. So with L is equal to 1 micrometers, so my W0 is evaluated to 11 micrometers. So with this, we have identified the geometries of the first stage of a two-stage op-amp. Next thing is the identifying the device dimension of the second, that is our common source amplifier stage, that is identifying M5 and M6 dimensions. So the rule of thumb is very simple. So in order to, because the second pole is contributed from the second stage, so we want that whatever the pole which is contributed, right, it is the second pole, it is contributed from this particular GM2. The expression is GM2 by CL. So this, if this GM2 is very large, which means the pole is very far from the unity gain, very far from PL, P1. So we have to choose this GM to be very much large. So the how to do is it is required second stage. So that is possible if the second stage carry a much larger current. So approximately it is 5 times of the current in the first stage. So if accordingly the current in the first stage was 40 microamperes, so the current in the second stage will be 5 times, that is nearly 200 microamperes. So that is the thing. So when that is the case, so the dimension of 6, that is M6 will be, so the dimension of this transistors will be 5 times of current. So dimension will be multiplied by 5 times. In the same way, as this dimension is by 5 times, this is I naught by 2. So this particular transistors will have 10 times of the current in M4 or M3, so that the dimension of this particular transistor M5 will be 10 times of dimension of M4. Okay. So with that thing, so that we have a better phase margin, so that we have M5 and M6 are evaluated to 110 micrometers, because you can see here I have 11 micrometers, 11 into 10, it is 110 micrometers, and the dimension of tail transistor was 9 micrometers, so it is 9 into 5, so 45 micrometers. Okay, so evaluating all the dimensions and identifying the GDS, so you can identify GDS by for the particular current and length. So we achieve the DC gain of around 60 dB, greater than 60 dB. So with L is equal to 1 micrometers, because for analog design we keep L to be large. Okay, and these are the different transistor dimensions. It is M0, MC0 is 9 micrometers, M1 is 2 micrometers, M2 is 2 micro, M3 and M4 are 11 micrometers, M5 is 110 micrometers, M6 is 45 micrometers. Fine. Now, so but there is a problem here, as you know that the Miller capacitor CC introduces a right hand side 0. So in order to cancel that particular 0, so we must have this type of a setup where this RC will eliminate that 0. So that is possible by introducing a resistor. So choosing the value of RC, which is almost or greater than equal to 1 by GM2. So I'll choose my RC to be 1 kilo ohms. Fine. So is the design procedure clear? So any doubts in the design?
Are there any questions about the design procedure? It might have been a little overload, but the file has been shared with you, so you can just go over it slowly. Yeah, Mayur, I think you can continue with the design. Let's simulate and see how the design works.
Okay. For the simulation, it's very important to have this simulation setup. So because the DC operating point in this particular two-stage op-amp is at a defined point only if there is a negative feedback. So in order to ensure the negative feedback for the DC, we'll put a large resistor and a large capacitor. So in case of a DC, what happens? This particular feedback is established, and when we are doing AC analysis, so this feedback is broken. So in case so this becomes because of this large capacitor, so the 4 is shorted, and this feedback is open, but still the DC point is established within the op-amp. So this is very important. So this is the simulation setup we should use when we are analyzing for the determining the phase margin, or that is when you are doing an AC analysis. Fine. So first we'll simulate this particular two-stage op-amp with this configuration. Okay. So let me show the netlist. So this is already shared with you. Okay, is the netlist visible?
Yes, it is.
Yeah.
So, by the way,
Uh,
this netlists and everything has been put up on the web page. Please download and simulate it in in your computers.
Okay. So yeah, this is differential underscore amplifier. So yeah, you can see here I've included the model file here. So you have to add the model file also. Okay, so then only you can instantiate this. So this the same nodes I have used here. Determine the netlist here. So CC is 2 pico. I was RC as 1.5 kilo ohms. So now dot control. So you can see OP will give me the different operating point, and I here I am printing all the required DC operating points for different transistors. Okay, so using print at M naught, it will print the values of VTH, GM, ID, GDS. Okay, so here I'll do the AC analysis. AC decade 50 points from 10 hertz to 100 gigahertz. I'll plot the whatever the magnitude in dB for node voltage 8, because this is what the voltage I want. Fine. Then I'll convert for the phase. I'll plot the phase in degrees. Fine. So you'll go to the ngSpice folder. Okay, so where I have my uh, netlist here, two stage underscore OTA with RC. Along with that, in the same thing folder, I have my TSMC model file. uh, 1 minute, where is yeah, you can see a TSMC Spice model. So this is that model file which is shared with you. So dot model CMOS and NMOS. For NMOS, CMOS N is the model name, and for PMOS, CMOS P is the model name, and these are the different parameters. So it's a level 49. So these are the oxide thickness. Okay, the VTH not without any effects. Okay, fine. So let's go to the ngSpice thing, and just type the file name with .cir. Okay, and then enter. If you see here, so I'm getting different operating points here. So for an individual transistors, M0, M1, then M3, M5, M6. Okay. Then if you observe the plots, so you can see here my op-amp, it has a gain of around 68 dB, 68 dB, and with the unity gain frequency of around nearly to 10 megahertz. Okay. Then coming to the phase response, so this is my phase plot here. So at 10 megahertz, so you can see here the first dominant pole is coming. After that, it is becoming flat, and then it is decreasing. So at near 10 megahertz, the phase is around minus 118 degree, so which is almost equal to 60 degree, right? So I think you can now download the Spice file and you can start executing. So any doubt in the this thing?
Uh, yeah, Purnima is asking whether we get the recording of the spice. Yeah, I'm recording this meeting. We will put it up in the same on the same web page. Uh, pl- Please
Hello,
try
hello,
to
sir.
execute yours on your computers the files which has been given, so that at least you can be sure that your setup is right and you understand how to set it. Yes, Mr. Dipesh, please go on.
Sir, on the figure window, can you put some cursor, something like that? In figure window, simulation result.
Yes, yes, we can place cursors. In fact, if you can just click at some point, it will directly print in the Mayur. Okay, yes.
It will print here.
Oh, direct.
Yeah.
Yes, good.
So what you can do is the first thing is will determine the so you can observe the phase response for different values of CC and RC. So after doing that, we'll see the small signal behavior. So you can just download and just execute it.
Mayur, can you just go over the lab questions once, so then we can leave it free for them to see.
Okay, fine. So I'll execute the next one thing also, sir. Fine.
Oh,
Okay, so next thing will be analyzing the small signal behavior. So for this, we'll apply a step input of 5 millivolts for this particular configuration and see the step response. Okay, so we will use this particular setup where the output is connected here, and the step signal of 5 millivolts is applied over 1.25, or you can apply on a given input common mode voltage range. So uh, yeah, so this is the netlist here. So you can see here I have given a step signal of zero point 0.9, okay, which is going from zero point 0.9 to 0.095. And let us see when the op amp is connected in unity gain configuration, how does it behaves. So yeah, so this is the, you can see the ringing here, small this thing, and then it settles. So it goes from zero point 0.9 to 0.905. Okay, so this, it can be improved by changing your resistance values. Okay, so here I have given this thing, right? Yeah, the ringing is reduced here, right?
so all that we have done, I think, is Mayur, if I'm right, we have just simulated the first time without the zero cancelling resistor,
Yes, yeah,
and second time with. So as we
with
can see that once you put the zero cancelling resistor, the phase margin is expected to improve, and that is what is seen in the step response. Once the phase margin is better, the ringing is reduced. Yeah. Uh, Thanks, Mayur. I
yes,
think, see, this is, it is a little difficult for us to conduct lab sessions online with these kinds of setups. So it requires some effort from your side to install and try fix the netlist on your side. We have tried our best to provide you example codes for simple circuits and given you some exercise problems. Please try to simulate them and solve the exercises that are being given. These are simple things, just like, for example, change the capacitance, see what happens, remove the zero cancelling resistor, see what happens, and simulate and try. So we have tried to give as detailed write-ups as possible for you to simulate the netlists and circuits yourselves. We hope you will take effort and simulate them. And if you have any questions, we are always here to. We'll try our best to address and solve your difficulties, whatever you may have. So, has everybody been